maximum likelihood of the exponential distribution, where we're going to use that formula as the exponential distribution. Um, so following the outline of how we calculate the maximum likelihood uh, estimator, what we do is we take a sample of data, x1 through xn, that's independent, and then the likelihood is given by the product of the density function evaluated at the observation x sub I. So because we know the parameterized distribution uh, of f of x, we plug in that formula for f of x, so we get lambda times e to the minus lambda sub xi, and following the rules of exponents, this translates into this formula. Now, we want to find the maximum likelihood, so to make our lives easier, we take the log of the likelihood function and determine where its maximum occurs. So taking the derivative of the log of the likelihood function, the log of the likelihood function will give us this formula, and then we just differentiate with respect to the unknown parameter here. So we don't know what the value of the parameter lambda is. So we differentiate with respect to lambda, and that gives us n over lambda, because the derivative of the natural logarithm is 1 over that variable, so n over lambda. Now the derivative of lambda here is just 1, so that gives us this term here. Okay. Now we solve for lambda, and it's going to give us this. That's exactly 1 over the average, where the x bar is the sample mean. Okay. Now, one thing I just want to comment on is that sometimes instead of having lambda, people will put 1 over lambda or 1 over beta as the parameterization, and that will change the estimate. So if you use a slightly different formula for the maximum likelihood estimator, you're going to get a slightly different estimate. Okay, so just keep that in mind. So this code here, what it does is it fits different values of the exponential distribution, so different values of lambda are shown here, to this data that's generated from an exponential distribution. Now, the true value of this exponential distribution has a scale of 3. Okay, so lambda is 3 here. Okay, and we want to estimate what the value here is that we should estimate according to this data, according to the randomly generated data from 15 data points. Okay, so we can see that this distribution here that comes from an exponential isn't consistent with the data because it wouldn't be very likely to observe these large observations. Excuse me, it wouldn't be very likely to observe these many observations that are small. So that's the problem with this flat one. Okay. Now this distribution that's dashed right here, it has a high probability of observing these small distributions, but the problem is that wouldn't be very likely to observe the large observations. And this red line is kind of the one that's most likely to have the data generated from it. Okay. Now, what this does here is we have the data points here and the histogram here, and we're going to fit different exponential distributions to this data. We're going to play it, okay? And the question is, which one best fits the data, okay? Okay, so you can see that that very last distribution, which turns red, best fits the data. It's most likely to generate all of the data. And it's the one that's shown right here, and that is the maximum likelihood estimate, which is calculated according to this formula. And it has a value of 2.14.